Okay, good morning to all of you. In today's class, we are just going to see different types of instruction set architectures, and then we are going to get familiarized with MIPS instruction set, so that in the next class we can take on the task of designing an ALU using the MIPS instructions, right? Okay, what is an instruction set architecture, which I explained in the last class? It has got two purpose, right? Firstly is suppose an hardware engineer he makes the processor. Okay, first he decides what kind of processor is to be made, and accordingly as per the design specifications he makes a processor, and then he provides a set of ISAs for the software engineer to write the programs, right? So the ISA essentially will be restricted by the kind of processor he has designed, right? So if he is using an RISC processor, if he has designed, then accordingly the ISA would change. If he has made some other processor where only 2-bit operands are permitted, only register to register transfer is permitted, or from a memory to register is permitted. So depending on the kind of hardware which he has implemented, so the ISA instructions he would give a set of ISA instructions which the software engineer needs to adhere to. Okay, so that is one way of looking at it, but we are probably going to approach this course in the other way around in the next two classes. Here what it's going to be done, the software engineer is going to write the ISA, and he is going to decide what kind of a processor he requires, whether it is an RISC or a complex instruction sets. So he is going to write an ISA, and accordingly the hardware gets implemented. Okay, so here he will write for the application which is intending to he will select what kind of an ISA he requires, and accordingly he writes the ISA, and that is finally synthesized into an hardware. So this is the second approach, and we are going to focus on this second approach from the software point of view, and we are going to implement the hardware as per the ISA, right? Now for that we need to have we need to know what kind of ISAs are there, and what would be good for a particular application. So in the next 3-4 slides we will see a little bit about ISA. Okay, so there are different types of ISAs. ISAs can be classified into a few of these subdivisions, which is first is the arithmetic operation. So addition, subtraction, multiplication, division, square root. So these are only some of the examples, which is arithmetic operation ISAs. Similarly you have logical operations like bitwise logical and or XOR or not. And what does bitwise means? Suppose I have an 8-bit register, right, like A0 to A7, and similarly I have an B register B0 to B7, and when I do AND A0 B0, the AND will be done between those two bits, corresponding bits. Similarly A1 B1 and B1 C1, like that. When you are doing a bitwise logical operation, there will be two datas in either in two registers or a register in a memory, and the corresponding bits like B0, B1, B2, B3, or for a 16-bit data B16 and A16. So those kind of bitwise logical operations will be done. Okay, so that is known as logical operation. Similarly you could have shift operations, right? So there are two kinds of shift. One is known as logical shift, and other one is known as the arithmetic shift. Okay, in the logical shift left, the entire data will be shifted towards the left. Okay, so you can specify by how many bits you need to shift left. If I say shift left by 1 bit, then the MSB will be thrown away, and from the LSB side a 0 will be pushed in. Okay, that is known as the logical shift left. Okay, I can also specify okay, logical shift 4 times. So 4 bits will be 4 bits from the MSB side will be thrown out of the register, and 4 zeros will be inserted from the right hand side. Okay, so that is means shift left. The entire data gets shifted towards the left. Okay, similarly I can have a logical shift right. Okay, in this case also, like if I say logical shift, I specify a register and I say 5, then 5 bits from the LSB will be, the entire data will keep moving towards the right. So from the LSB 5 bits will be thrown out of the register, and from the left hand side, and 5 zeros will be inserted. From the MSB side 5 zeros will be inserted. So that is known as logical shift right. Okay, so similarly you could have an arithmetic shift right. So only thing is, in the arithmetic shift right, the sign of the data will be maintained. Like suppose the MSB is 0, which indicates a positive number. So as we are shifting right, zeros will be inserted from the MSB side. Whereas if I do an arithmetic shift right and the MSB is 1 earlier, so as you keep shifting towards the right, 1 will be inserted from the right hand side. Okay, that means the sign of the number will be maintained, and that is why it is known as arithmetic shift right. So arithmetic shift left doesn't make any sense right, because it will always be 0 which will be inserted. You can't insert 1, because that will change the value of the number itself. So there is no meaning of having arithmetic shift right, shift left. Okay, so it is always logical shift left, whereas logical shift right and arithmetic shift right, they are different. From the left hand side, from the MSB side, for logical shift it is 0. For arithmetic shift it will be the sign. The MSB will, if it is 0, zeros will be inserted. If it is 1, 1 will be insert. Okay, now rotate also. Rotate shift means like the number which is coming out from the say when I say rotate left, say if I say rotate left, so all the numbers will be moved toward the left, and whatever number is coming out of the register from the left hand side, that will be again brought to the right hand side, and the least significant bit. And similarly, if I say rotate right, the number which is coming out from the LSB will be again fed to the MSB. Okay, so again you could have rotate shift with carry also. In the carry, so along with the register, the carry register also will be placed on to the left hand side of the register. Okay, so the carry also, you can suppose it is an 8-bit register, carry will become the 9th significant bit, and the entire thing will be shifted left or right as per whatever rotate left with carry or rotate right with carry. You can give those kind of instructions also, right? And then memory access. Okay, like if you have to fetch some data from the memory right into some register, you can say load. Right, load means it is loading the register from the memory. Store means you are storing some data into the memory from the register. So these two commands will be used for loading some data from a memory into the internal register of the CPU, and for storing the data from the internal register of the CPU to the memory. Okay, so that is what, and you can have other set of instructions like in out. Okay, in out is nothing but whenever the microprocessor is connected with input output devices, then also some data can be given to the through the in out. Right, load and store is transferring of the data from the memory, right, and from the internal registers to the memory, whereas in and out is transferring the input output data from the right, from the registers to the in IO devices which are connected. Right, so it could be a printer, or it could be an monitor display, or in could be an input from an keyboard or mouse. So these are the kind of ISAs what we have. Then you could have control transfer instructions. Okay, what is control transfer instructions? like jumps, right? So when you are writing a program, once you encounter some condition, you might want to leave the program and jump somewhere, okay, and execute some subroutine, okay, some other program, and when that program gets over, so in the end of that program you can write a return, so it will come back. So these are all some of the control transfer instructions. We'll see some examples. Similarly, you could have floating point calculations like LDF, ADF, okay? And then you can have interrupts, okay. Now what is interrupts is whenever a microprocessor is running, okay, so there could be n number of peripherals which are connected to a microprocessor. So whenever they want to communicate, and they will send an interrupt signal. So you can have the microprocessor will know, okay, this IO device wants to communicate with me, so it will, wherever it is the program is running, so it will temporarily store it will make a temporary halt to that program. It will store those addresses somewhere, right? Because an interrupt has come, so it has to now service the some device which has called for interrupt. So it will store the present data of the registers and the program counter into the stack, and it will go and execute the interrupt request, and then again come back, right? So that is known as interrupts, right? So one way, if you have n number of IO devices, there is something known as polling, right? Polling is nothing, at frequent interval you keep checking whether, okay, these devices do they want to send data, or you keep checking. Okay, so in that case, it is an inefficient way of doing it, right? You continuously keep checking if there is an input from keyboard, from their mouse, okay, from some other device. So that is known as polling. Whereas interrupts is another, microprocessor keeps doing the work which it is doing, okay. It doesn't keep checking, only when some request is made, a specific request is made in the form of interrupt, then it will stop the program which is doing, and then it will go and do the interrupt. It will service the interrupt, and then go back. Once it is done, it will go back to the program. So these are some of the ISA types which are there, okay. Okay, are you following Rajni, Deepa, Narendra, Nandarpuli? Okay, are you all with me? Yeah. Okay. Okay. So now if you see here, there is something known as instruction set and architecture. There are different types of instruction set architecture. Okay. So just for those who have joined late, and let me just tell you what is the target today. Like what we said, we are going to understand some instruction set architectures today, okay. So that once we know the instruction set architecture, then we can write programs, okay. So accordingly the hardware will get implemented, okay. So there is two ways of looking at ISA. One is the hardware engineer makes an hardware, and then he gives an ISA, okay. So the ISA is dependent on the kind of hardware he has implemented, and the software engineer accordingly writes the program, okay. Now we are looking at the program at this problem from a VLSI design problem from a different angle. I know what is the application intended for as a software engineer. So I am going to write a program, and using compiler I am going to make an ISA architecture, and that is going to be made into an hardware, okay. So we are going to just get familiarized with the ISA instructions today, and we are going to design an ALU in the next class using the ISA, and see through a compiler, and we make an ISA, and then we will see how the CPU is getting implemented, okay. So that is the task today, right? So there are different types of instruction set architectures. which we can decide, okay, what we want. Okay, so so depending on the architecture what we decide, so accordingly the hardware will get implemented. So so this is one is known as a stack architecture. This is very rarely used. It was used only in JVM, Java Virtual Machine, in which ALU has got only inputs from an stack register. Okay, so so you have the it takes first data from the stack, it will compute and it will give back the result to the stack. Okay, and then you need to have other instructions from memory. Whatever you want to execute, you will keep bringing it to the stack in a serial manner. Okay, so everything happens through stack out here. So hardware wise, this is you have to this is only one stack and one ALU, but then you'll have to keep getting the data from the memory to the stack. So this is one kind of architecture which we can think of. The other one is known as accumulator architecture. Okay, in this, if you see, there is one accumulator. Okay, accumulator is nothing but an internal register within the CPU. So memory is external to the CPU, right? From here, see, one data will be brought from the memory, and ALU will do the operation, and the second has to be the accumulator. Okay, accumulator is a register, and the result will also be stored in the accumulator. So this gives a slightly more flexibility than the stack. So from memory you can keep getting data, whereas the result will be in the always will be the accumulator, and from if required you can transfer the data from the accumulator to the memory, and also from the memory to accumulator also you can do that kind of transfer also. So this is known as accumulator architecture. So you have Z80 and 6502 ISS which use these kind of architectures. Okay, and this is the architecture which is which we learnt in our previous class, which is 8086, and which is most widely used. So all the Intel processors today from 8086 till date, they all are using the register memory architecture, in which you have an arithmetic logic unit. There will be some internal registers, and there will be a memory. So you can do an arithmetic operation between a memory and a register, also between register and a register, and the data will be in the in that register. Okay, so one register data will be overwritten out here, right? So that I explained in one. There is some advantage in overwriting that data, right? When we discussed earlier, if you remember, 2-byte ISA and 3-byte ISA, there were some advantages of a 2-byte ISA, and hence 8086 and these people, they have one of the target data is again stored in one of the registers. Like if I do A plus B, then this, A gets rewritten by the sum, whereas the contents of B remain same, right? So one register will get updated with the result. Okay, so that is how an register memory architecture. Okay, so when I say register memory architecture, it could be register operation also, right? But one has to be register. Okay, that is compulsory. Okay, you can't have two memory operations. Memory is not permitted. Register or register memory. Okay, these are the operations which are permitted. Okay, now if you see, this is known as only register. Okay, so in this case, whenever whatever is there in the memory, that needs to be brought into two registers, and then you give it to the ALU, and the result is again stored in the third register. So this is again now being very widely used. So all the RISC type ISAs use this architecture. So most of our mobiles and portable devices, they are using RISC type ISAs, and slowly many even for the desktop operations and desktop PCs, actually if you see, there is an the cores, small cores are all RISC only, but they support sys commands also, because those sys commands internally are again going to be you can write sys commands, but what actually the CPU does is it breaks that converts those sys commands into small RISC commands. So modern day processors are although we call them as sys for the PCs, but actually for pipelining we saw that the RISC processors are pretty easy. Pipelining is very easy for that, and that is the reason when you have so many cores running in parallel, so they are all actually small RISC processors, and whatever CISC instruction you give, that is again decoded into small RISC within the CPU. So although you can from the top level you could call it as a CISC on a CPU because it accepts CISC instructions, but practically modern day CISC registers use small RISC cores. Okay, so that is how this is the most important one, which we are going to do in this particular course, because we are going to do all the programming based on the register architecture. Okay, so now we are going to get familiarized with something known as MIPS instructions. Okay, now what is MIPS? Is microprocessor without interlocked and pipeline stages. It's a family of reduced instruction set and RISC instructions, developed by MIPS. So MIPS is an actually it was a company, and now it has been they have renamed it as MIPS Technologies. Initially it was MIPS Computer System. It's an US based companies, but they developed this, but this has been now universally being adopted for all RISC ISAs. Okay. So that is the reason we are going to study about this and try to write programs in using MIPS instructions and implement ALUs. Okay, that is what we are going to do in the next 2-3 classes. Okay, so just this we covered in the last class, but then let's just have a relook at this. So what it is doing is, like, you have an ALU. Right here, all the operations all the two inputs have to be from the register only, right? Or you could have a register and an immediate, like you can write, you can have an instruction from the instruction memory also. It is possible. From the data memory it is not possible, but from the instruction memory, like for example, if I want to write some data into a register, some specific data, say I want to write into the memory 10,000, that is an immediate figure, right? So that can be done. So that is why you have two mugs here. So one input is coming from the instruction memory, and the other input is coming from the register. So you can have either register or one register and one data coming from the instruction memory. Okay, that is load immediate kind of write immediate, add immediate. So those kind of commands we are going to see. So in those cases, the data from the immediate, and now the result of this is also going to go back to the register. It cannot go back to the data memory. Okay, the result. Okay, the only time the ALU will provide a data to the data memory out here, if you see here, is when sometimes we need to calculate the data memory, right? When we say we need to load data into some specific memory, right? We will see that the load memory instructions, at that time ALU will compute the memory location. So this signal will actually go and tell the data will activate that particular address. Okay, whereas the data will get transferred from the register only, right? So there is no way a data get transferred from ALU to the memory. It is always from the register to a memory, right? But ALU will give an address to the data memory. Okay, that address will be processed by the ALU and given to the data memory. So that function, and also there will be a program counter which keeps an track of the actual program which we have written. So it will fetch the program from the memory and keep executing that, and slowly it will keep, the counter will keep increasing, telling okay what is the next line to be executed. So this keeps an track of where the program is currently running. Okay, so that is what this is the overall rough block diagram of an RISC processor. Okay. Now if you see the MIPS instructions, they could be three types of instructions: memory reference, ALU, and branching. Okay, we are going to see each of them in detail now. But before that, understand this is what the beauty of RISC is, that now any instruction, whatever may be the case, it's all 32-bit. Right, whereas we saw that for an CISC it could be vary from 2 bytes to up to 16 bits, so in some processors. So the instruction set is it is not uniform, the length of the instructions in a CISC architecture, whereas in an RISC you will find all the instructions, whatever instructions you write, they do only small functions, but each of these instructions, whatever it could be, the entire instruction set itself is not very huge. It could be from somewhere from 60 to 100, that's all, and each of them will have only 32 bits. That means 4 byte. So each of that, whether it could be memory reference or ALU or branching operation, all of these will have only 32 bits. Okay, so that is the beauty of the MIPS instruction, right? So we'll see in detail again this in after a few more slides. So if you see here, when I write like load or store, okay, data like load into this dollar means it means the it is the serial number, okay, and then T0, like load data into the T0 register, or like store data into the T0 register. So these are the kind of instructions which you can give. So similarly you can give add instructions between two registers, and the data will be stored in the third register. Okay, it will add contents of T1 register, T2 register, and stored into T2. Or it could do a branching operation, that is it will compare these two registers, and then if it is BEQ stands for equal, if they are equal, the program will jump to this memory location. So these are the various kind of, we'll see this in details. So what I just wanted to show this slide is, so the CPU does these kind of operations. Okay, one is it does the address calculation. When I say a load command to the CPU, it is not going to load the data from the register to the memory. It only does the address calculation. Whereas like we said here, so if I go here, okay, this does the address calculation, and data will be stored from the register to file. So when I say a load, it does the address calculation. When I give an arithmetic or logical operations, it does the data operation. And when I write this branching equation commands, then what it does is it compares two datas, and accordingly it updates the program counter value, so that it jumps to the corresponding new address depending on the condition that has been satisfied after comparison. So these are the kind of instructions which is done by the ALU. Right. So in MIPS instruction there are actually 32 registers. Okay. So the first register is 0. In fact, you can't write any data. You can only read from this register, and it is permanently 0. Okay. So this is one register. And then some of the important other registers are, we can use these registers for other normal our programming, but whereas these are like specified, we use this last 4 for specific purpose. The rest of the thing this is reserved for operating system, whereas these registers we can use, right. The register number 31 is for return address, that is whenever we call for a subroutine, suppose we are encountering if register A and B, that the contents is okay, you jump to some other place to do some other task. So there once you are jumping, right, before the jumping, now you are moving away from the main program and you are going to do some other program, and then you are coming back, right? So when before the jumping, the present address, right, it will be stored in register number 31. It's not the present address, what has been executed, what next needs to be executed. So you are interrupting a program using a jump statement, right? So the present, after completing the present instruction, it will do a jump. So before going to the new address, the next, when I come back, I have to start again the previous program, right? So the current address of the program counter, that will be stored in the register number 31. Okay, so that is known as return address, right? So this is a stack similar to what we have in 8086, and a frame pointer pointer is the IP pointer which we have in 8086. That is where the current program is running. Okay, so that so when I write the jump instruction, the frame pointer data gets updated, because now you have a new program starting from a new address, right? So you have these are the kind of registers which are there in MIPS. Now let's see some of the instructions. So now if you have any doubts in any of these instructions, please let me know, because you need to be clear about all these instructions. Only then we'll be able to write an MIPS program for design of ALU in the next class. So let's try and understand some basic instructions. Okay, so you can write an add, subtraction, and or XOR. Okay, so these are some of the arithmetic and logic operations, and then you specify the register, a destination register, and the source register, and one more register. Okay, so what it does is, it will do this. When if I say add, the contents of RS register and RT register will be added, right, and the result will be stored in the RD register in the unlike in 8086, if you see here, and it will be RS and RS, right? You just specify two registers there, right? So the contents of the once you do an add operation, the contents of the RS gets destroyed and the new data comes here. So in an MIPS instruction, if you see here, okay, no content is overwritten. Okay, so it is always you are doing operation between two registers, and at the end of the operation, that data will still be there as it is in these two registers. Okay, the net result will always be in a third register in a so there's no data destruction which is happening here. So you're not losing out any data in these kind of instructions. Okay, the result is always stored in the destination register, which is different from the two registers on which operation is being done. Okay, so that is the major difference between 8086 and the MIPS instructions. Okay, one of these major. Okay. Then you could have several shift operations. Now it is shift logical left, shift right logical, shift right arithmetic. Now you have this is the destination register, here is the target register, and then you have then this is the format. You write the by what amount you want to shift it, right? So if I write say register number 1, register number 2, and if I write 1 here, so the contents of RT, okay, that will be shifted towards the right by 1, since I have written here by 1 bit, and the data will be stored in RD. Okay, here again it is important, like in 8086. Okay, here itself the data gets one data will be pushed into the LSB, and from the right it will be thrown away. So the RT gets updated with the new shifted data. Here it is not happening that way. Here this RT data will remain as it is. The shifted data will be available here in the destination register. Okay, so that is again a major difference with respect to 8086, right? So if I write say register A, register C, and I write 4 out here, then then whatever was the contents of here say C, it will be shifted by 4 bits, and then that shifted data will be written into RD. Okay, so you can say it that way. First this data will be copied into RD, and then the shift operation would happen, so that the data in RD is not disturbed at all. Okay, so that is the kind of operations which we can do. Right now, if you see here, all the registers in MIPS are 32 bit, right? So maximum shift you can do towards left or right is 32, right? So if it is 32, then I can here I require 5 bits, right? So corresponding to if I have to shift it by 32, then 2 to the power of 5 I have to give here, right? 32. So that is the reason out here, right? SA is a 5-bit data. Okay, is it understood why it is a 5-bit data? Because the maximum size of these registers is 32 bits, right? So I have to just give the data how many times it has to shift towards the left or right, right? Is it 1 time, 2 time, or 32 times maximum? So that is the reason this is just an 5-bit data out here, right? Similarly, I said we can have an add immediate. Okay, so this is known as add immediate. Okay, and target and then you have RT and RS and the immediate. Okay, what it is going to do, immediate you can give when 16-bit data. You can't. RS is a 32-bit data. The target where the sum will be stored will be 32-bit, but the immediate value which you are going to provide, that is only restricted to 16-bit. Okay, so I can write an add I A B and then a 16-bit data. So and 16-bit, that whatever 16-bit data I write, that will be added to the contents of the register B, and the result will be stored in register A. So if I write A B, and if I write say 32, for example, I write here 40, then 40 will be added to B and the result will be stored in RT. So this is known as add immediate. Okay, so if you see here, if I go back here, right, so that's what I said for these immediate instructions, like the one data could be the register, the second data could be from the instruction memory itself. Okay, so this is where the immediate, when I do add immediate, that what is the value to be added, that will be there in the instruction memory, right? That is not available in the register. So that is why we employed two mux here. So that is where this comes into operation. Right, so add immediate. Okay, so the 60 now when the 16-bit data is immediate, is sign extended into 32 bits. Okay, sign extended means the 16-bit data, if the most significant bit is 1, then it will be first converted into the rest of the significant bits will be made into 1 only. Okay, so that the sign, suppose for a 32-bit, if you see the 2's complement method, what you have learnt in an digital bit, then suppose it is say minus 10. So for a 16-bit, the minus 10 will start from 1 to all 0 and then some values. Okay, for whatever it is, right? Now if I have to convert that minus 10 into 32-bit data, from the 17th bit to 32-bit, I have to put all ones. Okay, then also it will continue to remain minus, the value doesn't change. So it is, if you sign extend it. Okay, now if it's a positive number, the MSB will be 0. So rest of the all and the 16th bit will be 0, and you put from the 17 to 32 also 0. So it will continue to remain a positive number. If it is a negative number, then the 16th bit will be 1. And you need to, when you are extending it, sign extended means from the 17th bit to the last bit also you are going to put it as 1 if the MSB is 1, so that the sign is saved. Okay, the same sign is extended. That's known as sign extension, and then you do the addition. Okay, if you put if it is 1 and if you put zeros here and then do the addition, then it will be considered as a positive number. So the value of that number, whatever 16-bit signed number which you have given here, so that gets wrongly computed, right? So you can't do that. So it is sign extended. Okay, so that is what you need to remember, right? Okay, then there are some ALU instructions, like you can also do AND immediate, OR immediate, XOR immediate. You need to mention the result, that is RT, where the result will be stored. Okay, here the source register, and then you write it data out here, immediate data. You specify and immediate data. Okay, again here it is the unsigned number. Okay, it is an 16-bit unsigned number. Okay, you got to remember that. Okay, so AND operation will be unsigned number, and only the if you are doing it with an RT and RS with an immediate number, so the MSBs, they don't from the bits 17 to 32 they don't get disturbed. Okay, so whatever is the immediate data which we are writing in this command here. Okay, so we write only 16-bit of information. So the first lower 16-bit of the source register, bitwise an operation would happen, right? And bitwise an or this. So the first 16 bits of the data which you are providing will undergo an AND or an XOR operation with the lower 16 bits of the register. Okay, here if you see here, it is 0 is extended. Okay, so that if you are doing an 0 into the next, the 16-bit immediate data is 0 extended into 32 bits. So it is not that sign extended. So whenever we are doing these operations, okay, logical operations, right? This is not an arithmetic operation. So 0 will be extended. Okay, so say for example, if I put an 16-bit data, right, and then if I do an AND operation, so invariably in the destination register, the LSBs will all be zeros, right? Because it is all 0 extended, so they will all be zeros. Only the in the LSB, whatever is the data which was there in the source register, so it is basically you are truncating the data of RS. So suppose RS is a 32-bit information, right? If I do an AND information with so all the MSBs will become 0 if I do an AND operation, right? If I AND immediate operation, because the 16 all the MSBs you are doing an AND operation with 0, so they will become a 0, and okay, so that would happen. If you do an OR operation, then whatever was the MSB bytes from 17 to 32, they will get as it is into the RT. Okay, if you do an OR operation, right? If you do an XOR operation, then then things will be slightly different. Okay, so similarly you have one more instruction which is known as LUIRT. Okay, that is load upper immediate. Okay, so if you see here into an register, if we have to get some data from the memory, right? Immediate means getting it you have to load some data into an register. Then we can only load the data into the it is a 16-bit, right? We can load the data starting from 17 to 32 bits only, right? We can't do direct write any data directly into the lower portion of the register. We can only write an instruction LUIRT into and then we can specify an 16-bit data out here. Those 16-bit data will get returned into the upper portion of the register. Okay, so that is what LUI RT means. Okay, so suppose I have to do an if I have to write 32-bit information, then what do I do? So although I have written it here, I will explain this in the next after 2-3 more slides. So how this is how we can write 16-bit data into the higher bits of the register. Okay, so you can't write into the lower bits. Suppose I have to write a 32-bit, then what do I do? Now if I have to get this 16-bit data into the lower portion of the register, then after loading it to the higher portion, then I need to do a shift right operation. Okay, 16 times, then only it will come to the lower portion. Okay, so that is one way of doing it. So you will to get a data, now remember, to get a data into the lower portion, you will require two instructions. One, put it into the higher 16 bits and then move it by 16 bits towards the right. So that is how you will do it, right? And then you have some memory reference instructions. Okay, that is load into the register. Okay, into this register. Now offset RS. Okay, so this is how the syntax goes. Like what is offset RS is RS is the register. Okay, one register. Okay, and offset is an value which you give. Okay, so the CPU now what it does is it loads the data 32-bit data from a memory location whose memory is calculated by adding the 16-bit offset what you have given to the 32-bit information which is available at this register. Okay, at the RS register. Okay, so when I write load RT offset RS, that means into the RT register some data from the memory will be returned, some 32-bit data from the memory will be brought and returned into the target register. Okay, that is what. From which memory will I get it? Okay, that memory will be calculated by the CPU. How will it calculate? So it will add two things. One is the 16-bit offset which you are providing in this instruction, and you are specifying the RS register. So whatever is the contents of the RS register and the offset, okay, that will be added by the ALU, and then this register. So this will see ALU will just compute the address, and then from the memory locations the data will be brought to RT. So that is what I had explained here also here. So the whenever I write the load command, so the address will be calculated by the ALU and it will be given to the data memory. So it will activate that particular cell, and then that data will be brought into the register out here, right? So this data can only be brought to the register. So there is no link between the data and the ALU, if you see here. Okay, so the data cannot be used directly for ALU computations. It has to always be brought into the register only. Okay, so that is what this instruction does. Right. Okay, similarly you can have an store instruction. So this does the opposite of what we learnt in the load instruction, in which you RT and then you write an offset. So whatever is the contents out here, right, in the RT register, that will be stored into this memory location, and again here also the memory will be computed by the ALU, okay, by adding the offset value what you have given to the register which you have specified. Okay, so you need to specify the register and the offset. So it will do a simple addition of these two and generate the memory location, and in that memory location the contents of RT will be returned. So this is known as the store RT command, right? Then you have some commands like branching. Okay, so BEQ stands for branch if equal. Okay, so what it does is it compares. So this is the syntax RS, RT, and then label. Okay, so RS and RT, it will compare the contents of RS and RT, and on equal it will jump to the program will now the program is sequentially running, right? Now the moment it encounters this command, and if this condition is met, Okay, that if suppose this data is, if this condition is not met, it will just go to the next instruction. If this condition is met, then the program counter will be updated with a new memory location. Now it will go and start operating a subroutine, or it will jump to that program. Program counter will essentially jump to a new address and it will start executing from there. Okay, so that is the where will it go? At the new location again. That is also, if you see here, okay, label is a 16-bit that is an 18-bit signed constant. Okay, so this could be 18-bit a signed constant, remember that. Okay, and 16 it is an 16-bit signed data. Okay, the new address will be computed, okay, by shifting this data towards the right. Okay, so what the ALU does is it is adding an 18-bit sign constant, like the 16-bit whatever information which we have given, it will shift it towards the left by 2 and then add to the present instruction. So that will give the new location. Okay, suppose I am in 10,000, okay, in some location, say corresponding to 10,000, and I give here as 1,000. Okay, so it will shift 1000 by 2 bits. So right, so the shifting by 2 bits is actually multiplication by 4. Right, if you see here, so if I shift that, I am giving here 1000, decimal 1000, it will shift it by 2, so it will become an well, if you see, if you are shifting, say if I say 2-bit data, right, if it is say 10, it is 2. If I shift it by 1, it will by towards the right 1, it will become 100, which is 4. That is 2 into 2. Right. If I shift it by 1 more, it will become 100. It is 8. So every shift left operation is actually multiplication by 2. So once we have given an 16-bit number, it shifts it to the left by 2 bits, and then it adds to the present location. Okay, so that is what the jump. Now it is signed because you might have to jump towards the back or towards the front. So that's why it is an signed constant, right? So you can always want to go back in the program somewhere, or you want to skip some lines and go forward. So both is possible. So accordingly you need to give the label. Okay, so remember here, label is not the absolute value where the memory is where you need to go. It is just a relative offset from the present value. Okay, so it is just an offset value which we are providing, right? So if it is already in 10,000, from 10,000, would you want to go further by 1000, or if you have to go further by 2000, or if you want to go back by 500, if you want to go back by 100, so that kind of an offset is being provided here, right? So that is known as a label. Okay, so similarly you could have an same instruction which is known as branch if not equal. In this case again the syntax remains almost same. Only thing is, if these two contents are not equal, it will jump. If they are equal, it will just simply skip the label and the jump instruction and just execute the next line of the program. Okay, if it is not equal, right? If it is equal, if it is not equal, then it will jump. So equal, and if when we write programs, you know that whenever certain conditions we need to check, so these two are known as the branching operations. Okay, so again you have one instruction which is known as an jump to target. Okay, so here we are specifying the address where straight away we are not telling the we are not giving the offset value, but we are telling the J target, the exact location where the program needs to jump, and we are not sorry. Here what we are doing, we are not checking for any conditions. Okay, we are not checking for any conditions. The moment you write jump, simply we will straight away jump to that new location. So you are not checking the condition. Here it was conditional jumps, like you are checking the condition whether they are equal or not. Here this is unconditional jump. Straight away it would jump. And where will it jump? To the, now again here you write an PC, right? So target whose 28 bits are the 26-bit target. Okay, so here you are going to put the 26-bit data that will be shifted by 2 bits, and in that particular address itself, here again you are not providing the offset value, you are providing a 26-bit data, right? So if you see, the total instruction set will be 32 out here, right? Here you are providing the 16-bit data out here, but the total instruction set here will be 32. Similarly, here also the total instruction set will be total number of bytes for this instruction will be 32. I'll show you one more table to clarify this aspect. But then when I write jump target, and although this particular immediate values, here I am giving an 16-bit data, here I am giving an 26-bit data, but that doesn't mean that the total instruction size will change. Okay, the total instruction size will continue to remain as 32-bit. Okay, so I have an 26-bit data which is being fed here. It will be shifted to the left by 2 bits. Okay, and then and it will go to that particular address. Okay, so that is known as jump to target. And then you have an jump, AL, jump and link. Okay, in this case it will just jump to the next target. Then the program counter would change, so it will start executing that particular program. Okay, and then at the end, then it will continue going as per whatever you have written there. Okay, but in some cases, like jump and link, in which it will go to like generally when you call for a subroutine, it will go to the subroutine, and at the end of the subroutine you want to come back to the main program, right? So you need to save now where you have left the main program and you have gone to the subroutine. So that value of that current program counter needs to be stored somewhere. Okay, so when I write JAL target, it will go to the target destination, but before that what it does is the present value of the, now this is being the present value of the program counter that is being executed, but the next program will be available at PC plus 8, so that data will be stored into the register number 31. So it will, so that what happens is, whenever in the subroutine, when you say return, okay, then the moment in the subroutine you encounter the statement of return, okay, the program counter will be loaded with this data, okay, which is there in 31. Where and what is in the register 31? Earlier, before jumping, we had stored the next memory address of the main program, right? The next instruction where it was residing. So that particular memory address. So the program counter will now get updated with the memory address from where we left earlier. Okay, the next memory location from where we left, so that again the main program continues from here. Okay, so that is the reason we call it as an jump and link. Okay, so that is the difference. Okay, now suppose this is another jump register. Okay, RS. Okay, in this case what happens is the jump register transfers the target address in the register. Okay, so suppose you are done a jump register, and you are going to, you are writing an subroutine. Okay, in the subroutine, and so you don't have something known as a return. Okay, so what we do is instead of a return, jump RS will be 31. Okay, so since we have done, when we do RS30 jump register number 31, okay, what it does is, so at the end of the subroutine you write this, so that so before coming to the subroutine, in 31 this address was stored, right? So again the program counter will be updated with the data which is there in the 31 register, right? So that is how this is known as, like in 8086 we have seen a return command, right? So this exactly does that. So instead of return, we have the jump R. Okay, jump R means jump register, and here, so we need not write so if you have to return back to the main program after an JAL execution, then we write 31 out here, right? Register number 31. Okay, so this is what is generally used for in lieu of return in the MIPS instruction set, right? So if you see here, these are the various instructions. These are the 32 bit, right? So if you see, so for add, so 26 to 31, they all will be 0 for these instructions. Here will be the like a register number. There are 32 registers, right? So 32 registers means 5 bits will be required to declare each of this register, right? 0 means 0 register, 1 means 1 register. So if I go back here, here we said there are total 32 registers, right? 0 to 31. So if you see here, each of these registers, they will take 5 bits. So this is 5 bits. This will be 0, 5 bit, 5 bit, 5 bit. And these are for the format for the add. For subtract, you write a different number out here. For AND, you write a different number out here. For OR, for XOR. But if you see, all these instructions are only 32 bits. So here you define the register numbers. These and these columns remain 0 out here. And then you have these numbers varying. So once this instruction is fetched and decoded, so ALU will be told what is the kind of operation which requires to be done. Similarly, for shift operations, you have here these 3 shifts. These are 0, 0. Here we said the 5-bit data is required, whether to tell how many times it has to shift, right? So if it has to shift for only 1 or 32 times, so maximum 5 bits will be required here. So these bits will 0 to 5 will indicate how many times it has to shift. Now if you see, for shift L and for these 3, this data is going to change, right? So similarly, you have all these different. So for all of these things, if you see here, here it is we said it is 16-bit data, right? Add immediate. So from 0 to 16, this is it will be 16-bit data. 0 to 15 from here to here, right? Immediate means these are all 16-bit data. So this will be the add immediate, and first a few bits will be like this. Okay, this will be the source register, this will be the target register, and then 16-bit data information. So the total will again be 32-bit, right? So that is how. Now here we said it will be like for these cases, the address lines will be, if you see for jump, what we said, it will be 28 bits, right? Whose target address 26 bits needs to be given here. So if you see here, only this much is given here, and this total 26 bit address will be given here. So again the total comes out to be 32 bit. Okay, so irrespective of what instruction you use, the total number of bits required will be 32. Okay, so that is the beauty of the MIS instructions. Okay. And now there are, over and above that, there are some assemblers. Okay, assemblers are not actually, what it actually does is just to make the life of a software engineer a little more comfortable. Let me go back to that slide. Here these are compilers. Okay, so when we are writing an software like ISA, okay, there are certain additional instructions which is not actually an ISA, a slightly higher level instructions, and the compilers understand, and they use that instruction will be broken down into ISA finally. Okay, so the hardware recognizes only ISA, but the compilers can recognize certain high level instructions also, which will be broken down into small ISAs. Okay, so that is what we are going to see here. right here, right. So a NOP, right, no operation, right. No operation means like it doesn't shift left operation for the 0 register, and it will move it 0 time. Okay, so nothing would happen. Okay, but why do you require a no operation? Sometimes you require delays, right? So suppose you want to insert some time delay into like you are reading some data. You don't want to keep reading every second. You want to keep reading only after every 1 minute. So you need to insert some delays in between. So you can use these kind of no operation. So it will just consume some time, but no operation would happen, right? So that is one. Similarly, another is Lee. Okay, it means load immediate, which can load a 32-bit immediate register. Actually, I just told you earlier that there is no way you can load 32-bit data into a register. But and at the assembler level, I can write that Lee. Okay, what it actually does is like it splits this into 2 different instructions. Now, if you see here, it is first what it is. If I want to do Lee 4, like in the 4th register, okay, it dollar means okay, wherever we write this means the register number. Okay, so into the 4th register I need to put this number. This is an right 32-bit data 1 2 3 4 ABCD. Okay, 0x means whenever we write an 0x, it means that this is an hexadecimal number. Okay, so we prefix it by 0x. Okay, and so that the computer knows what follows is not a decimal number but an hexadecimal number. Okay, so 1 2 3 4 ABCD. So 1 2 3 4 needs to be written into the higher register. Okay, so I can simply write first to write 1 2 3 4. I can write LUI, load upper immediate. So this is this cannot be understood by the this is not an ISA, but the compiler will split it into these 2 instructions. LUI 4th register, then I write 1 2 3 4. So this 1 2 3 4 will get loaded into the upper register, upper 16 bits, right? And then I do or okay with with this register with 0x ABCD. Okay, now when I do an OR operation, OR operations happens with the, so when I load this data, the lowermost data, all these will be zeros, right? So only the upper register will get data written as 1 2 3 4, and this will be 0 0 zeros. And then when I do an OR operation after that with ABCD, so the next lower 4 hexadecimal numbers also get written into the register. That is the lower 16 bits also data will be written. So if you see here, when I write Lee in the compiler, it will execute 2 different ISAs. Okay, one is load upper immediate and then OR immediate. Okay, so it will take this first 4 data, first 4 16 bits from this data and do an load upper immediate, and it will take the next 16-bit data and do an OR immediate operation. So these are some of the, so there are a few other such instructions. This is a no operation, right? And a clear, move, not, and a sub immediate. Sub immediate is also not actually available. So only add immediate is available here, but in the compiler, in the language, when you are compiling, you can write sub instructions. What it will do is write 4 and 5. Like 5 for doing 5 minus 1. Okay, I can't have what I can write is 5 and then minus 1. It adds this. Okay, so the if I write sub 4, the target register is 4. I have to delete 1 from the contents of 5 register. That is what sub I want to do, right? So what the compiler does is it will write an add I 4 5 minus 1. So these are some of the instructions which you can have a look of at your own time. So these kind of instructions also the compiler understands. Okay, so I am following this book. So you can see where you can get this book, either soft copy or a hard copy. and this is for the next 2-3 lectures. So this is written in the things are much more written much in better clarity wise. I found this book is gives much more clarity than your prescribed textbook. So I'm following this. Otherwise, whatever for your examination point of view, whatever is being discussed in the class, that will be good enough. But if you want to further get in-depth knowledge, then you can refer to this book. It's a good book worth buying. Okay, thanks a lot for now.